Okay, I'll start by telling you a little bit about my motivation with this talk. The charge that I got is here, and there's a bunch of things in it, and including talk about the algorithms, but also lessons learned, how you're going to do things in LSST. And I made a decision that weak lensing being kind of not of general interest, I'm not going to dive into the gory details of algorithms. And another reason to not do that is that we actually have multiple algorithms, and each would probably take a full talk to do any justice. So I decided instead to focus on lessons learned and what we're actually going to do for LSST. How are we going to apply those lessons learned, and how are we actually doing our work? Uh, and here it says to maximize scientific return. From hearing the previous talks, I realized that maybe that's not what people expected, and I'm sorry about that. I think a lot of people were hoping to see gory details, but I'm certainly happy to answer any questions either after the talk or on Slack. So I'll talk about first the challenge we have, then I'll go into lessons, and I don't mean these lessons as, everyone should do exactly what I say. More, these are the things that actually influence us day to day when we are doing our work now. And so in that sense, I hope that they're interesting to everyone. And it does explain a lot of the reasons we're doing things the way we are in LSST. So after the lessons, I'll dive in to what we in Desk are actually doing for weak lensing shear measurement. So the challenge, I think, is pretty extreme. We've set the bar extremely high. We want to make full use of the data set we're going to get, and it's going to be a very rich data set. And so an example of this is we think in order to fully use the data that our weak lensing measurements need to be accurate at about the 0.1% level, which is pretty amazing. Just for comparison, at the time of writing, the most accurate measurements in the literature are only claiming 1 to 2% on real data. So it's a big, we need to make a lot of progress. And this is not unique to weak lensing. This data set is going to, if we want to use it fully, means very tight requirements for many probes. And in my opinion, the way I look at this, in order to meet these goals, we're going to have to put forth a huge effort. I think everyone understands that. But I think probably we're going to need to embrace novel ideas, things that we have not considered before in order to overcome challenges. And maybe more than ever before, we'll have to work with what I say here, great discipline. And what I just mean by that is 0.1%, you can't fly by the seat of your pants. You have to actually be really careful. And again, I don't think these things are really surprise to anyone, but that's the challenge. Part of the charge was to discuss precursor work. I'm going to put this into the lessons learned. I've personally worked on a bunch of experiments, and the people I work with in DS, for example, have experience in also in other surveys as well. So the question is, what have we learned from all this previous work? And how are we going to apply this knowledge to our work for LSST? And again, I don't mean these to be preachy or like you should do things differently or whatever. This is what's literally driving us day to day. So this is more of a cultural thing. Identify the critical problems that are unsolved. And I specifically mean here algorithmic problems, which we must solve to succeed. And there are a number. And once you've identified these, what we need to do is dedicate as much resources as possible to solving these algorithmic problems. And one of the things that I think we've learned over the years is that this actually requires some convincing at all levels of the organization. And a corollary to that is spend as little time as possible on the solved problems, and I'll say a little bit more about that later. And just a quick example from my own experience, and this is not meant as a criticism, this is something I went through personally, and we went through in DES. It was proposed in 2003, and at that time we actually thought we were pretty close. We thought we would have a weak cleansing method that met our needs. Now it's 2020, and I think everyone agrees that it's still not fully solved. Only recently have candidate algorithms been introduced that we think can work in principle. And over this time, we've had sort of at most a few people dedicate, or a few persons worth of time dedicated to this. And with hindsight, we probably should have dedicated more effort to it. In LSST, I think it's a similar situation. I count 1.3 FTE, and this is to make existing algorithms work in LSST, not for research. On the other hand, we understand a lot more now. We actually have good reason to think that we have excellent candidates. But it's a situation where that if we do fail in this regard, then we have to fall back to calibration simulations. And I'll say a bit more about that later. So this is a big challenge. And this is this corollary. If there's something out there that works well enough, use it. Don't spend time on it. I think it can be painful to adopt other solutions that you didn't create, because they won't work exactly how you want them to. But given that there are actual unsolved problems out there, I think better to just adopt something if you can. Now getting to more technical things, aggressively test all algorithms with validation simulations. And this isn't just meaning, I think everyone uses simulations, but I think a particular aspect of it that's important is to build them up in such a way that you can toggle all of the relevant features independently if possible. So for example, you want to turn on all features one at a time until, hopefully from simplest to most complex, until you find a problem which you try to fix, or eventually you reach full planned simulation complexity and the algorithm provides acceptable accuracy. And this actually is, I think people do work this way. It wasn't how we began working in my experience in the past, but it would have been really useful too. And this requires a fair amount of dedication and effort, and I would say it can equal or exceed the work that you actually spend on developing the algorithm. Furthermore, each test you're going to do with these simulations has to be as precise as the expected precision of the actual measurements, actually more precise. For example, at the end of the day, it's totally reasonable to say, I want to be confident that there's no bias in my validation simulations with 99.7% confidence. And I think this is necessary, but it can be quite resource intensive, both people and computing. Another thing is kind of maybe a minor point, but actually day to day, this has been important for me and my colleagues, is don't think about 1 sigma, think about something bigger. You're going to run thousands of tests, literally, and 2 sigma fluctuations will be seen regularly. And in fact, I just this last week saw a result move by 3 sigma. And of course, this applies to data analysis too. This is kind of, hopefully, I don't even have to say this these days, these are software problems we're talking about. These are algorithms. So use best software practices. And this means everything should be unit tested. And you shouldn't be able to commit to the master repo without going through continuous integration that runs all the tests. So here's a point that I think has been really important and not realized by me until recently. Confirmation bias is even more relevant for these validation efforts than they are for real data analysis. The process itself is by definition iterative. You're going to run a simulation, look for problems, try to fix it, and rerun. And in this process, it is remarkably easy to subconsciously create a situation where either in the simulation or the analysis of that simulation, you've artificially given yourself a zero bias result just without even realizing you've done it. And part of this is that we tend to stop when we measure no bias and move on to the next test. And I actually don't know how to combat this. I don't have a systematic way to combat this except through diligence. I mean, I've thought of ideas like we could try to have two completely independent software package or simulation packages, for example, one that cannot be influenced by the testing results. But I think this is actually not practical because so many of the pieces that go into a simulation package are inevitably shared. And how are you not going to update your simulation package based on what you've learned? It's actually, I think this could actually require some more thought. Currently, we're taking the be diligent approach, and we hope it's good enough. Now, we're running these validation simulations, trying to get to 0.1% level for lensing and whatever percent for other probes. But there still might be some bias at the end of the day for whatever reason. Either you might have a good reason to think that you can't fix a certain bias. It's possible. Or you might not have time. And if you can imagine, we're running up against the year 1 cosmology deadline and we just don't have time to fix a certain problem. For lensing, we don't have any absolute calibration sources. So we would have to probably have to correct with a simulation. But how would you approach such a correction? It's kind of, could be kind of scary. And one of the lessons here is that calibration simulations are harder to do than good data analysis. Often with good data analysis, you don't need to understand everything you've done. You don't need to understand everything that you measured or how you measured it. And a good example is absolute photometric calibration. We don't do that by simulating the camera and all the instruments and everything that we can. We calibrate to a reference source. But if instead you need a sim for calibration, like we would in lensing because we don't have absolute calibration sources, and if this correction were large, you really have to know what you're doing. We would need to understand everything we put into that simulation, and it must match the real world very well. And this gets back to the earlier point. What this really means is we should put as much effort as possible into developing algorithms that require small corrections. If the correction is 0.5%, we'll be much less sensitive to inevitable errors in the simulations that we're using for the correction than, say, if we had a 10% correction. Okay, so that's the lessons. Now I'm going to talk about what we're actually doing in DESC for weak lensing shear. And so first I'll give the big picture of what we are doing without going into many details. And then after that, I'll give some details about different parts, and in particular, trying to connect them back to the lessons learned. And then I'll show some results at the end. And what is it that we're trying to do here? Why are we doing it? So DM needs the community to deliver state-of-the-art algorithms. And shear algorithms are still an area of research. And so the way that we're doing this in DESC, of course, there can be volunteer efforts and they're welcome, but currently the main efforts are due to pipeline scientists. Myself, Matt Becker, and Bob Armstrong are all working on implementing existing algorithms for this. And what we plan to do is deliver at least 2 algorithms. We'd love to deliver more. One is BFD. I'm not going to go in, as I said, I'm not going to go in details. Bayesian Fourier domain, and the other one is meta calibration. Bob Armstrong is working on BFD, and Matt Becker and I are working on meta calibration. I'm not going to go into details of the algorithms because I think they're not of general interest. They would take a lot of time. Just to say that we think they're very promising and they're worth the effort to work on this. So what I'm going to talk about is what we're doing to make these work for Rubin Observatory data. A big part of this is co-adding. As has been discussed a lot, this is an important problem, and how we do them affects all of our science, and this is true for weak lensing as well. For weak lensing, we think, well, what we're doing and what we think is the right thing to do is to co-add in small regions of sky. And the reason for this, there are many reasons, but one of the reasons is that for lensing, we need a continuous PSF because we need to correct for the PSF. And discontinuities are hard to correct for. So we need it to be continuous, and this means that we can't do a co-add that has edges in it. So if there's a visit CCD image that has a boundary crossing the region, we can't include that. It would cause a discontinuity. And so we'd have to remove that from consideration in the co-add, and we would waste a lot less space, a lot less data if we use smaller regions. So typically we're thinking of smaller regions than the current co-add size. And I want to make a couple of technical points about this for the aficionados. We don't make them too small for meta calibration because in order to correct some biases, we have to control for detection effects, which means we need to rerun detection on certain process versions of these images, in particular ones where we shear the image. We've kind of settled on about an arc minute, but this is not optimized. And just for stack aficionados, we're hoping that eventually we can just redefine the patch size and rerun the COED code. But currently we're just using arbitrarily defined regions in the existing code, the one we're working on now. Another aspect of this is getting the PSF right on the COEDs you do, which means co-adding the PSF also. And in particular, we need to co-add the PSF exactly the same way that the COED images are co-added, at least statistically. And this is different than exactly what the stack is currently doing, and I'll talk about that more later. We need to propagate noise images through exactly the same way we propagate the images through. Image resampling that we do for co-addition, it produces correlated noise, and the interpolation of bad regions produces biases as well as correlated noise. But fortunately, algorithms such as BFD and meta-calibration can deal with these issues if we propagate a noise image through all of the exact same processes. And we've actually tested this, and we can get an unbiased result at the end, all else being equal. Just a little bit of detail, BFD actually wants to include the noise from undetected sources in this estimate, but as going to come out in a paper soon, the covariance matrix that they would derive from the noise field can be updated afterward with measurements made on the real data to account for these undetected sources. So and for Medi-Cal, we just want to use a background noise field. So we can use the same noise field for both efforts. For detection, we want to detect as deep as possible. So we're going to do a combined multi-band currently it's a straight coed, R plus I plus Z. And then we do multi-band processing after that. We process objects across multiple bands. And at this stage, then BFD and meta-calibration are working separately. We hand off coads and noise fields and potentially a detection catalog. So now getting some details. So how are we applying the lessons? I think that's important to connect back, and how is this work going? All the code, this is just I think an important point, but I can just say quickly, all the code that for working with the stack that we've written and that we will write, the meta calibration code, the simulations, everything's on GitHub, heavily unit tested with continuous integration. So we're putting our money where our mouth is. We're trying to reuse existing solutions as much as possible. We use the stack for everything we can. We plan to take as input the calibrated exposures, the CCD images. We use the stack COED code, stack PSF, stack detection, stack WCS. I'm sure there are other more things that I haven't mentioned. When we can't use it, we're going to try to feed our solutions back. For example, we had to write some code to include subpixel shifts in the PSF coedition. This probably didn't matter too much for photometry, but it's important for weak lensing. The resampling caused a small amount of blurring of the PSF, and we need to really get this it has to be fully reflected in the PSF. And this everything was in there, what they were doing, but except the subpixel shifting. And we've got something that we can feed back in to the stack. It's not currently possible to propagate noise images through cosmic ray interpolation, just for technical reasons. We're going to work with that. And so we're doing our own noise propagation and interpolation, but we're going to work with DM to make this a stack feature. And eventually we're going to need to mask bright stars. We don't know if this is going to have to happen at the pixel level or downstream. We hope we can pull this code from HSC potentially, but we may need something custom. But whatever happens, we're going to make sure that it is as available as possible to everyone. What about the aggressive testing with validation simulations? So we're developing the image simulations in parallel with the analysis code. And a good fraction of our time goes towards these simulations. And we are implementing them in such a way that every feature can be toggled independently. And just some list of these things. We have the dithering rotations. We have tan WCS with variations in the pixel scale and the WCS shearing. We need more realism here with astrometric distortions. We have cosmic rays, simulated cosmic rays, bad columns, realistic galaxy size and magnitude distributions with this weak lensing to blending package, which uses a bulge disk AGN model. We need more morphological complexity, but actually with these modern algorithms, it's not actually critical for most of the testing, and we haven't been using it yet, but we will put it in. We have realistic multiband star magnitudes in colors, and importantly, realistic galactic stellar density variations. So each simulated image draws from draws a realistic density from the distribution we expect for the 18,000 square degree survey. And I got these from Javier Sanchez, so this is basically falling from DC2. Currently very primitive star saturation and fake bleed trails. This is something that we can update very soon to include the examples that were from the same codes that were used for DC2. Jim Chang is helping with that. Here's some example images. This is example galaxies, and these should look familiar to people who have used this package before. These go much fainter than the detection limit, and have the appropriate density and distribution of properties. And we also, here's an image with artifacts and stars, and this shows some simulated cosmic rays and bad columns, and very fake looking bleed trails around the bright stars. But on the right here shows an example of the kind of stuff we're going to be putting in next. And these are important for lensing because we're going to have to deal with these kind of problems. So what are the current results? So we have all this stuff in there, and we have been turning features on one by one, and using very broad confidence regions so that we don't get fooled. And on the plot on the right just shows an example series of tests where we start from the simplest thing, not even using any of the previous code, or only using code that we had previously from DES, basically. Then turning on a bunch of features and using the stack. And the idea here is that we should be able to turn all these features on and not see a bias outside of this central dark band, which is our requirements, roughly our requirements. Also, there's one that sticks out here, and that was an intentional situation where I turned on something I knew would cause a bias, and it should, and it did, and we understand why. So this is the kind of testing we're doing, with these long series of very big simulation tests. We're discovering some things, which is good, and stuff we're going to have to deal with. Here's an example where it looks like high stellar density is causing a bias, and we need to either understand it and fix it, or think about what we're going to do. So the plot on the right shows the calibration bias. Basically, this is a fractional bias on the final signal in a weak lensing signal as a function of the limiting density that you allow into the survey. So we run simulations where we draw from the expected stellar density for the 18,000 square degree survey, and then we apply a cut to that, only including up to 100 stars per square arc minute. So nothing is going in higher than that. And this shows that a bias, there's a bias at 100 if you allow in fields with 100 stars per square arc minute, and it decreases when you make cuts. And this is a bit of mysterious to us because I have done tests before that would have indicated the bias should be the other sign and actually be much smaller. So this is something we're gonna have to figure out, and so we have work to do. So I'm actually not sure what time it is because so I guess I'm a little ahead of schedule. Huh?
You're fine for time.
Yeah, I'm ahead of schedule, I guess. We're fine. So in summary, it's going to be extremely challenging. And I can say specifically for weak lensing, it's going to be extremely challenging to fully utilize the data that we're going to get. We're doing our best to apply the lessons we've learned from precursor surveys to this data set. And we've already begun, and we're working diligently on this. And I think things look very promising, and I hope to report back excellent results soon. Thank you.
Thank you, Erin, for that set of very important lessons learned. Can we have a round of applause for Erin on Slack, please? So we have some questions queued up already. We will start with Jim. Just a second.
So I was curious about your point that you felt that DES would have benefited from more effort devoted to shear measurement algorithms earlier, and I was curious both on whether the degree you thought that needed really existing expert effort versus new to the field graduate student, new postdoc kind of effort, which is of course easier to come by, and then whether you had any thoughts on being able to transform the newer effort into the experienced effort by teaching people as you go.
Jim, I think you've hit on the crux of the problem, really. I didn't bring it up because I thought it was, I thought it was too fine a point, and I thought it's maybe too difficult to answer. As you point out, if you can get experts, people have been working for 15 years on this, you're going to you're going to bring in a lot of expertise and make progress quickly. And also they'll know how to begin working on what needs to be worked on. They just have a lot more experience. But as you say, it's hard to come by. And I think that's reflected in the LSST current effort. And then, so the other option is to bring in young people. And as you say, there's this issue that there's a long time to bring them up to speed. So I think we'd have to adopt the latter as much as possible. We have to try to bring in young people and teach them and mentor them and get them up to speed, and also ensure that their effort is worthwhile to them down the line, so they can hope to benefit from this, to put it frankly, on the job market.
Okay, so the next question we have is from Conrad.
Hi. Hi. I noticed that the two preferred methods that you're implementing are not the kind of most intensive model fitting methods like M3 shape or lens fit. Is this I mean, I'm sure this is a conscious choice, but are you giving up on model fitting methods completely?
Well, currently Medi-Cal, the version of Medi-Cal we're using is model fitting. What we rely on is that we don't need to use a complex model with meta-calibration. We can use pretty much anything we want. So we don't have to adopt anything that's accurate. It can be terrible, and we can correct it. So currently it's just a Gaussian fit.
Mm-hmm.
But we're certainly not going to try to do anything that would add additional computational complexity and time, unless we think we need it, and we may need it. So, and there are technical reasons we may need it. For example, in order to make corrections for selection effects, for example, to put objects into a photo Z bin, you have to use quantities measured by meta-calibration or by images created by meta-calibration, sheared images. And it may be that it's worth it to us to spend a little more computation time, have a little bit more higher failure rate, for example, and use a complex model if it helps our photo Z binning. BFD does not use any models, and it doesn't need to, as I think you know.
Sure. Okay.
Does that answer your question?
Yes, thanks.
Okay, thanks.
Okay, next we have Paul Schechter.
Erin, nice talk. I know you've put a lot of effort into the PSF for DES, and you said in the process of your talk, don't work on problems that are solved problems. How do you feel about the state of the PSF for DES at the moment? Is it a solved problem as far as DES is concerned? Is it a solved problem for LSST?
Well, I'm not as expert as other people on the line, Mike Jarvis, for example, and others. We think that in the bands we're using in DES, RIZ, we think it's good enough. I know that. It's not good enough in GE, so we're not using G. I don't know, I think from Mike's talk that he would indicate that in the redder bands, we may be good enough already for LSST. But it'd be good to get, if we can unmute Mike and let him respond, or so he could just write it into the chat and we could all read it, or something like that.
The reason I picked you out on this is because I've been working with data which refers to Sheldon corrected PSFs. And so evidently you played a substantial role in this at some point.
I wonder what that is.
There were bad PSFs and now there are good PSFs.
Oh, okay. I'm not sure. Are they?
Liz Buckley calls them Sheldon, pre and post Sheldon.
Oh, okay. Well, I'm not sure.
Okay.
Sorry.
Okay, we have a question now from Arun.
Thanks, Erin. You said you use the calibrated exposures as input. I thought the shear was measured on the COEDs. So what exactly do you use that for?
Oh, well, currently we're making our own COEDs. So we take the idea. That's the idea, is that we take the calibrated exposures and COED them, but we don't want to use the main COEDs currently. And Jim has talked about how they would like to make the kind of COEDs that we're going to use. So I don't think this is a necessarily I think this is a temporary situation. Eventually, I think we could be just taking COEDs directly produced by DM.
Thanks.
So if people want, I can reply. So yeah, so in the year 3 DES analysis, the PSFs are by a long shot subdominant as far as systematic uncertainties go. We're not completely sure whether that's still going to be the case in year 6, so that's why I talked about some of the improvements we're planning. But we definitely have much larger problems than the PSF for recleansing currently.
We'll go out for LSST.
Yeah, so the quality that I showed on the DC2 is not good enough for LSST yet. So we definitely do have work to do at that, you know, that level of statistical errors that we're shooting for.
Okay, Robert, you had a question.
Yeah, I was just going to ask why you're building your own COADs. And Yusra tells me that it's because you're building edge-free COADs, the way Jim was talking about yesterday. But okay, so there's not something new and clever. It's just we haven't got around.
No, there's nothing new. We're using all the same code. We're just limiting what goes in, and we need to propagate through this noise field as well. So we're doing all that. But this is stuff that can easily be done on the DM side, I think.
No, I know about that work. So phew, thanks.
Okay, so if that's all for the questions, let's thank Erin again.